Hello friends, welcome to Mang.io channel. In this talk, we are going to talk about the load balancers. In today's distributed systems, load balancers are typically the entry point for most of the software systems as they allow you to scale your systems more easily and make changes to your infrastructure without negatively affecting your customers. So the content of this talk has been carefully crafted to provide you good amount of both breadth and depth to crack the system AI interview. So let's get started. We have full jam-packed agenda. So we'll start with a simple problem and then we'll try to solve that problem using simple DNS based load balancing followed by L4 and L7 based load balancers. Then we will talk about how we can deploy different load balancers to serve billions of users. We will also talk about various distribution algorithms that load balancers uses to distribute the incoming traffics to the backend servers. And then we'll also look into like self-managed software load balancers, hardware load balancers, and load balancers as a service. So let's get started. So now let's assume that I have a Monk.io web application that I have deployed to a particular IP address. Now when I want my users to connect to my application, like they usually connect with the domain name, so I went ahead and created a DNS entry that this Monk.io application is mapping to this particular IP address. Now when the user wants to connect to my application, they actually make a query to DNS to resolve the IP address. Once they get the IP address, they can connect to my applications and they can get the response. Now suppose that my application got very much popular and now hundreds of thousands of connections coming. I am not able to serve those requests using single instance of my application. So I went ahead and I created a separate application instance and deployed to a different IP address. Now that's how, even if I have deployed my instance and I have IP address, there is no way I can get the new request or a request route to my the new server. So now even if I have deployed another instance of my application, there is no way the users are coming to my applications directly. So what I have to do is that I have to register another entry in the DNS for this IP address. That is where the DNS based load balancing comes into picture. So what I'm going to do now is that I'm going to register the new instance of my application, and when user wants to connect to the application, right, and they request for a domain name, the DNS resolver returns the one of the IP address of the system. So it could be 99.1 or 99.2, and then the client uses those returned IP address to connect to those applications. The DNS can use return the IP address in the round robin way, or it can also return all the IP addresses and send to the client and let the client decide which IP address they want to use. So this is what the DNS based load balancing is. It's also known as DNS round robin. It's a technique for distributing incoming traffic across multiple servers using DNS. So instead of using a hardware or software load balancers to distribute the traffic, DNS based load balancing, it relies on the DNS to resolve domain names to multiple IP address, and each of which correspond to a server that can handle the incoming traffic. So there are different advantages and disadvantages of the DNS based load balancing. One, it is super simple, right? It is very simple to set up, requires no additional hardware or software. You just go to DNS and configure it. The second one is that it's a scalable in a sense that it can handle the large number of servers and clients. It can also work with any type of protocol. It could be HTTP, TCP or UDP. However, The DNS based load balancing has some limitation. First, it is not really very flexible. It can only distribute traffic in a round robin fashion, or you rely on a client to either randomly choose the IP address or return the first one without taking into account the server load or other factors. Second, it has no way of detecting server failures or taking failed server out of rotation. So for example, if my first instance is down, the DNS does not know that, right? So DNS will still be returning the IP address of the first one and the client will fail. So there is no way for the DNS server to detect failures. Another challenge is that it can lead to an uneven distribution of traffic, as some clients may cache the DNS response and continue to use the same server even if the other servers are available. So from here, so we have suppose two users, and one user is not very frequent user, so he just make a request to one application, he got the IP address of that. Now the second one make a request, he got the IP address of second, but the second one is a very heavy users and keep on making requests, and all the requests are going to land to the second one. The first is still not getting any requests. So this leads to the uneven distribution. So to conclude, overall the DNS based load balancing, it's a simple and effective technique for distributing traffic across multiple servers, but it is best suited for applications that can tolerate some unevenness in traffic distribution and do not require any advanced load balancing features. So now let's take a look at the server side load balancing. So here what I am going to do, I am installing my load balancer in front of my two web applications. So I have deployed my load balancer and it's a basically a proxy machine, right? So and its IP address is 99.3 suppose. Now, so I have deployed that load balancer. Now I'm going to register my two different application instance IP addresses to that load balancer, so that load balancer is aware of my two different instances of application. Now and then, as we did earlier, we are going to register this IP address of the load balancer to my domain name. So now my monk.io is actually mapping to the IP address of the load balancer. Now when a client has to make a request, right, so it goes to a DNS, it gets the IP address of the load balancer, and then the request client make a request to the load balancer, and the load balancer picks up the one of the IP address depending on the distribution algorithm that it is using. It will direct the traffic to the monk.io application instance 1 or 2. So that is how the server side load balancing works. So let's go ahead and we are going, so we have two different type of server side load balancers. So they, when we say two types, actually types is coming from at which layer of the OSI those load balancers works. So we know that we have 7 layers in the OSI model, and so a load balancer that works on the layer 4 is called L4 load balancer, and the load balancer that works on the L7 layer, it's called L7 load balancer. So now let's go ahead and take a look at the different L4 and L7 load balancers. Now let's take a look at the L4 load balancers. As we discussed, the L4 load balancer type is actually a type of load balancer that operates at the transport layer, which is layer 4 of the OSI model. It actually distributes the incoming traffic based on the information such as source IP address, destination IP address, and the port number. L4 load balancers, they do not inspect the content of the network packets or the application layer protocol. Instead, they use the information from the transport layer to distribute traffic to the appropriate server in the server pool. These four things like source IP address, destination IP address, and the source port number and the destination port number, they are also called as 4 tuples. And if you add a protocol into that, that's called like 5 tuples. There is only one connections per request, and when I say one connection means that, for example, I have a client and I have a load balancer. So client to the load balancer, and then from load balancer to the server, it is a single connection, right? So L4 load balancer, it creates only a single TCP connection for the request. So let's take a look at the uses for that. So they're often used for the applications that requires like high network throughput and the low latency. For example, like gaming and streaming services. The other uses could be like network in the network appliances such as like firewalls and routers. They provide the load balancing functionality to distribute the network traffic across multiple servers. It is also used in virtualization software such as like VMwares and Hyper-V that can use the load balancing to distribute the virtual machine traffic across the host in a cluster. Uh, it can also be used in the CDNs like the Cloudflare and Akamai. They use the L4 load balancers to distribute the traffic to their edge servers. One thing that is interesting is that it should not be used in microservices world. Why? So if you look at the microservices world, right? So we build the services that are serve very specific purpose. So for example, like you have the images service that serves only for the images. So you have videos, you have things, and what you need is that you the load since the load balancer it only looks at the L4 layer, right? So it does not read the application level information. So it does not know that whether the request is for images or it for videos or for some other purpose. So they cannot route the request to appropriate instance, right? So that's why the L4 based load balancer should not be used in the microservices world if the goal is to route the request to appropriate service. Uh, in general, since uh, they don't look at the content of the request, uh, they are generally faster than their L7 counterparts. It does have very less overhead because they're not reading the content. One not so good thing is that it does not provide any specific caching that application can use. So this is all about the L4 load balancers. Now let's take a look at the L7 load balancers. So as we discussed earlier, like L7 load balancers, they operate at the highest level of the OSI model, which is the application layer. And what does it mean is that they have the ability to inspect and manipulate the content of the traffic that is being sent to the servers. Right? Basically, they can read the content and they can modify those contents. And and that enables them to make much more informed routing decisions. Uh, the other thing that we can do is the L7 load balancer is it provides a caching. So by caching frequently accessed content like L7 load balancers, they can actually reduce the load on the backend servers and they can improve the speed and reliability of the content delivery. L7 load balancer they actually can cache the content at different layers of network such as like HTTP, TCP or SSL, right? Caching can be particularly useful for web applications that serve static content, like for example, like images, CSS files, JavaScript file. By caching this content at the L7 load balancers, the load on the backend servers can be reduced and users can enjoy a faster browsing experience. Now, it is a bit slower compared to L4 LB is because they can read and manipulate the content of the traffic. So since they are doing much more work compared to L4 load balancer, and that's why it comes with a cost that it is bit slower compared to L4. Uh, Now it creates a two TCP connections per request. So earlier, like we saw in L4, like we had a client to the load balancer and the load balancer to the server. They actually had been a one single connection. On the other hand, L7 load balancer, it actually creates two TCP connection per request. So client to the load balancer is one connection, and from load balancers to the server is actually another connection. So for every request, we have the two TCP connection. Uh, L7 load balancer could be an ideal for microservices world. The reason being is they can make much more informed routing decisions. right? They can actually look at the URL, they can look at the header, and based on that they can make a decision. For example, like if you have all images stored at all image related services present at some particular location, so they can look at the URL with a specific structure like regular expressions, and based on that they can route that request to your image service. Similarly, for example, like you have ordering service, the request can go to the ordering service itself. So it's pretty good for the microservices world. uh, the other L7 LB that can provide is SSL termination. So what actually the SSL termination means that usually the request from client to the load balancer is actually secure, like they run on HTTPS. So for example, like it's run with SSL. Now, if once the request reaches to the load balancer, the load balancer can decrypt that request and use that decrypted request internally in my data center. So that is also called like SSL offloading. So the benefit for that is that like you don't have to install like P904 certificates on each and every web server involved in processing that request. You can just install it on the load balancer, and then it will decrypt the incoming request, and it will encrypt the outgoing request. So internally those requests are not SSL, and it could be better for performance perspective also. Now let's take a look at how we can deploy these different type of load balancers to serve billion users. So we will start with a simple DNS based load balancing. So for example, like I am going to serve facebook.com and we have multiple IP addresses registered on DNS. One thing to note is that these IP addresses are not the addresses for individual machines. So let me talk about that a bit more. When the user make a request to a DNS to resolve the domain name, they get an IP address from one of those IP address listed in domain name. These IP addresses are actually the IP addresses for ECMP. ECMP is basically short form Echo Cost Multipathing. Think it more like an L3 level load balancers. It's basically router, right? So now when the request come to LCLP, which is L3, then it routes to the multiple L4 load balancers that we have deployed. So you can think I have tens of load L4 based load balancer that has been deployed. Now when the L4 load balancer request is received at L4 level, then it gets route distributed to multiple L7 based load balancers. Now so L4 load balancers could be in terms of like 10, 15 or something like that. L7 could be in terms of hundreds. And then each L7 load balancer could be serving thousands of VM, right? So with this is how the structure, how the deployment topology looks like if I am going to serve billion users. Of course, it is not a real right way, but the goal is like to give you a context or just an approach that how we can serve billion users. Now let's take a look at the distribution algorithm that load balancers uses to distribute the request to different servers. Here are some of the most common load balancing algorithms. Uh, like random. So this algorithm routes the request to a randomly selected server. This is like very simple and effective way to distribute the traffic, but it may result in an uneven distribution or uneven server utilization. The second common popular is the round robin. So this algorithm, it distributes a request evenly across all servers in a round robin fashion, and each new request is directed to the next available servers in a predefined list. Now the issue could be that if you have heterogeneous servers, like for example like one server is much more have much more capacity than other, then this algorithm does not utilizes that thing. So that's where the weighted round robin comes in. It's a similar to round robin, but with the addition of weighting the factor of each servers, and each server with a higher weight receives a proportionally larger number of requests. The next one is the least connection. So this algorithm, it routes a request to the server with the fewest active connections at the time of the request. This ensures that requests are distributed to the server with the least current load. Another one is the least response time. This algorithm actually measures the response time for each server, and it routes the requests to the server with the lowest response time, because it may assume that the lowest response time means that the server is much bit faster or much more stronger, so it will reduce the response time for the incoming request too. The other one could be simple IP hash. This algorithm calculates the hash value based on the IP address of the requesting client, and then it routes the request to the server associated with the calculated hash value. The benefit for this is provide some sort of like sticky session thing. This ensures that request coming from the same client is always routed to the same server. Now, these are the different distribution algorithms that we should be aware of, and depending on the situation or depending on the characteristics of your applications, you can choose like which distribution algorithm works well for you. Uh, Now let's look at the different categories of the load balancer that are available in the market. Let's start with the simple load balancers as a service. So the first one is like simple. Think this. Okay. So we can, at a very high level, we can say load balancers are actually two different types. One is like public facing and a private facing. Public facing means that this load balancer is reachable from the cloud. So basically, its IP address is actually public. Uh, so we can have different load balancers as a service, for example, like Amazon ELB or Azure Traffic Manager and load balancers. Uh, Azure Traffic Manager and the load balancers, they are both services. It's provided by the Microsoft Azure for managing the traffic to applications and services, but actually serve different purposes. Azure Traffic Manager is actually a DNS-based traffic routing service. It allows you to distribute the incoming traffic across multiple endpoints, such as like web apps, cloud services, virtual machines, based on a set of rules that you define. And it works by redirecting users to appropriate endpoint based on the criteria such as geographic locations, endpoint health, and performance. This enables you to improve the availability, performance, and resiliency of your applications by distributing traffic across different regions. Azure Load Balancer, on the other hand, actually L4 based load balancing service. It distributes the incoming network traffic across multiple virtual machines or VM skill sets within a single virtual network or availability sets. It balances the traffic based on a set of rules that distributes evenly across the available instances and improving the performance and availability of your applications. Now let's talk about the self-managed software load balancers. So there are two examples for that. Like one is the Nginx and second like HAProxy. Take a look at Nginx first. So Nginx is like primary web server that can function as a reverse proxy and a load balancer, and it is optimized for serving static content and can handle a large number of concurrent connections efficiently, right? And Nginx can also serve as a caching servers. Nginx uses an event-driven asynchronous architecture that allows actually to a large number of connections and relatively a very low resource utilizations. The other one is the HAProxy. HAProxy, on the other hand, have a very high performance TCP HTTP load balancer and proxy, and it is optimized for proxying the load balancers and supports like range of protocols like HTTP, HTTPS, TCP, UDP. HA proxy uses a single process like multi-thread architecture. In summary, both the Nginx and HA proxy, they can function as a load balancer and reverse proxies. They have different strength and use cases. So depending on the characteristic of your application, we can decide on which one to move. Uh, you can also go ahead and look at the documentation for Nginx and HA proxy if you are really deciding that which load balancer is suitable for your applications. Next, take a look. Let's take a look at the hardware load balancers. So, hardware load balancers are basically the devices that are designed specifically for the purpose of the load balancing network traffic. Uh, so, here are a few examples of popular hardware load balancer. Like we have F5 Big IP. We can have Citrix NetScaler. We have Kemp Loadmaster. So there are different hardware load balancers. Of course, like if you want to drill down further, you can just go ahead and look at documentation, but just knowing the name from the system interview perspective, I think it's good enough. On a closing notes, in today's distributed system, right, where we are dealing with a lot of users and data, uh, by default, I would recommend like having load balancers as an entry point for your distributed systems, as they provide a lot of functionality like over scalability and availability. So for example, like you can add more web servers at any point of time uh, to your system without your clients even realizing that you have added a new server, and the newly added server can start receiving connections. There is no propagation delay as when you use the DNS based load balancing. It also provides the automated scaling. One good thing about using the load balancer is that it makes your maintenance of server much easier. Like you can take a machine from the load balancer pool and wait for all the active connections to drain, and then safely you can install the operating system patches, update the software of the system, and then put it back to the load balancer pool. It does not affect even like a single client, and you can use this method to perform like rolling updates all over your cluster. So that's what we have for the load balancers. See you in the next session. Thank you. Bye.